All right, awesome. So we'll switch gears a little bit here. So I'm Sydney, I'm a postdoc in CISL, and I will be talking today about multi-objective optimization. Okay, so let's just kind of dive in here. So up until this point in the quarter, you've pretty much only been talking about single objective optimization problems. So basically, like, we can have multiple input variables to our objective function, but there's just like one variable that comes out the other end, and it's just like this one objective that we want to optimize. So we're going to switch that up a little bit for this lecture, and we're going to talk about multi-objective optimization. So we've switched this kind of this F to a boldface F now, and all that does is that means that we input multiple variables potentially, but we also now get out multiple variables, and each different variable that we get out here is a different objective that we're trying to optimize. Okay, so we can kind of look at an example here. So basically, this might look something like this, where our output here of our objective function now is comprised of all of these kind of smaller objective functions for different objectives. So like F1 is the first objective, F2 is the second, and so on, all the way up to n possible objectives here. Okay, so here's an example that's just like been on my mind maybe. So maybe what are some objectives that you want to optimize as a PhD student? So there's many different things that you might be trying to optimize throughout your PhD. One, maybe you want to do cool research. You also, at some point, probably need to write some papers. Here's an important one you don't want to forget about. You should try to maintain happiness. In addition to that, you also want your advisor to be happy, at least ideally, so you want to keep your advisor happy. And then, there's many other things you might go about trying to optimize, all the way up to like, you probably also want to graduate in a reasonable amount of time. Maybe you don't want to be here forever, although I still haven't quite figured out how to leave Stanford. Okay, and so these are all these different objectives that you might be optimizing as a PhD student. And some of them you can look at and they actually like align quite nicely. So, Michael always gives this example. He's like, if he's your advisor, like your happiness is directly aligned with his happiness. So if your happiness increases, his happiness will also increase, and we're all good to go. We can make both of these objectives better all at the same time. But there might be some objectives that are misaligned. So, for example, doing cool research and then graduating in a reasonable amount of time. Because typically it takes time to do cool research, and so there's only like so much cool research you can get done and also still graduate with your PhD. And so in this case, there might be some points where, the more cool research that we do, the less reasonable the amount of time it takes us to graduate. So more reasonable would be like in this direction, if that wasn't clear. Okay, and so there's kind of like a trade-off between these objectives, which is often like what we find in the real world. A lot of times when we're trying to optimize for multiple things, there's some trade-off between them that we're going to have to kind of deal with here. And so the way we typically talk about these types of trade-offs is with this idea called Pareto optimality. So a design, we say, is Pareto optimal if we cannot improve one metric without worsening another. So let's kind of just look at this example here and look at this point. Can someone tell me whether you think this point is Pareto optimal? Okay, so you're shaking your head. No, it's not Pareto optimal. Because we can move over to, for example, this point here, where we both do more cool research and we graduate in a more reasonable amount of time. And so this point here is actually not Pareto optimal because we can improve both objectives at the same time. But now we can move over to this point here. Do you think that this point is Pareto optimal? Yes, yeah. So now we can't both do more cool research and graduate in a more reasonable amount of time. And so this point is Pareto optimal. So basically, in this case, like higher is better for both objectives. And so when we want to know if a point is Pareto optimal, we can just look and see, like, is there anything both above and to the right of this point in our plot? If there is, then it's not Pareto optimal. If there's not, which is true in this case, then we can say that it is Pareto optimal. And then typically what people do is they introduce this idea of a Pareto frontier, which is basically the subset of all the designs that are Pareto optimal. So everything on this Pareto frontier here does not have a point that's like above and to the right of it. Any questions on that? Cool. So then let's look at one more example here. We're going to switch out our axes a little bit. Okay, and we're going to look at some different programming languages that are out there. And we'll look at readability on one axis and then performance on the other axis. And then we're going to introduce one more concept here that we often talk about with these multi-objective optimization problems. That's a concept of dominance. So we say that basically a design dominates another design if it is equal or better in all possible objectives. Okay, so to test your knowledge on this one, let's just kind of focus in on a couple design points here. Okay, so does Julia dominate Python? Oh yeah, I see some heads nodding. Obviously, of course it does. Okay, so if you're trying to pick your programming language in the future, you can refer back here. All right. Okay, so that was some like concrete examples. You can think back to those in your head as we go on if you want to have some concrete example in mind. We're going to abstract things a little bit now and just talk about, like, in general, what the math behind a multi-objective optimization problem looks like. Okay, so this is nothing new. This is what you've had this whole quarter. We have like some set of possible inputs for our optimization problem. And then up to this point, we've had this like single objective. And so the set of possible outputs is just like it's on some number line. It's just like one-dimensional. And we're just trying to find the minimum of all of those possible outputs. And so we're just trying to find this like single point here. But now we're switching things up, and we have this multi-objective objective function. And so now we have actually this kind of multi-dimensional set of possible outputs. It's not just like a line anymore. And so then you can look at this and you're like, well, what is the minimum? What are we looking for here? Like, what is the equivalent to this pink dot for this like whole set? And the answer is it's basically this Pareto frontier. So now we're not just looking for like a minimum, like this single point, but we're saying like, what is the Pareto frontier? What is the set of all designs for which we cannot make one objective better without making another one worse? Okay, so kind of our goal here then for this chapter is not just to find a minimum, but to actually generate this whole Pareto frontier. Okay, so how do we do this? So here's one super straightforward method. So let's imagine that we're designing a collision avoidance system, and we care about two different objectives. The first is the collision rate. So of course we want this collision rate to be low between aircraft. And the second is the alert rate. So how often do we tell the pilot to take some maneuver to avoid colliding? And so ideally we would have like no collisions and also never have to alert the pilot. Of course this is not feasible. And so what we could do is we could design a whole bunch of different collision avoidance systems and like compute these metrics for both of them. And so you can think of like each point on this plot is basically a different collision avoidance system that we designed. And now we can just take all the points on this plot and look at all of them and be like, which ones are not dominated by some other point? And then that will give us kind of an approximation of our Pareto frontier. And just to make sure you've kind of got your mind flipped right here, so in the examples I showed before, we were trying to maximize, which is not typically what you're doing in this class. So we were like looking for a Pareto frontier that'd be out here. We've switched now. We want to minimize collision rate. We want to minimize alert rate. For the rest of the lecture, for the most part, we're going to be minimizing. So flip your brain a little bit here. Our Pareto frontier is going to look like this now. Okay, so this kind of gave us a nice like approximate Pareto frontier. But the issue with this approach is like it's typically kind of wasteful. So there's all these designs here that we tested out that are like not on the Pareto frontier. So we didn't actually need to bother with them because there's always like a point that's better than them. And it doesn't like guarantee that we're going to get this nice like smooth, correct Pareto frontier because we're just going to get whatever designs we actually sampled. Okay, so then you're like, okay, is there a more efficient way to do this? And of course there is, because there's more to this lecture. So yep, there's a few of them. Okay, so to remind you our goal here, we basically don't get to see this like output set normally because to get a point in the set, we have to like pass our points through our function. So this would require like evaluating the function at every single one of our possible inputs. And what we want to do is just optimize the function to generate points on this Pareto frontier. Okay, so we don't get to observe the points on this Pareto frontier, and we're trying to find them, basically. So let's imagine we have this two-objective optimization problem. We have F1 and F2. And I'm going to introduce a whole bunch of methods now to actually generate points that lie on this Pareto frontier. So the first method that the book talks about is called the constraint method. And basically the idea here is that we're going to constrain one of the objectives in our multi-objective optimization problem. So for example, let's say that we're going to constrain the second objective here. So we're going to constrain F2. And we're going to say it's less than or equal to some value C2, which is some parameter that we pick. And then we can look at what this constraint looks like. So basically, we're saying that this F2, so our second objective, it must be less than C2. So we've got to be in this region at the bottom here. And then what we're going to do is we're going to turn this into a single objective optimization problem, where we're now just going to optimize the remaining objective here, which is F1, and then subject to this constraint. So we would solve this using any of the optimization techniques that you've already learned so far in this course, because this is now a single objective optimization problem. We know how to solve those. And then just visually, in this case, we can kind of just look at it and know where we would end up. So we're basically saying, in this region, what output of the function minimizes F1? So it's going to be the output that's furthest left here. So it'll be this output over here. And we'll get this design point. And then you can imagine, we just picked C2. So we could change up C2 and then solve this whole problem again. So let's change up C2. Then we'll end up with this point. And we can just kind of repeat this process, sweeping over this value that we constrained that second objective to. And then we'll kind of sweep out a whole bunch of points on this Pareto frontier. So that's one way to go about trying to generate the Pareto frontier. Any questions on the constraint method? Okay. Okay, so another method that's sort of similar here is called the lexicographic method. And the main idea here is we're also going to kind of convert to some single objective optimization problem. And the way we're going to do it for this method is we're basically going to say we're just going to ignore the second objective for now, or if there's more than two objectives, you just ignore the rest of the objectives. And we're going to say we're just going to minimize over F1 first. So when we do that, we're totally ignoring anything in this direction. We just want to minimize in this direction. And so we're going to get this point over here. We'll call that Y1 star. And then we're going to say, OK, now we're going to solve another optimization problem, another single objective optimization problem. But we're going to add in the constraint that the first objective is less than or equal to the point that we just found when we minimized our first objective. So we're basically adding this constraint here, and then we're going to solve now this minimization problem. So in this case, it's not super exciting because there's only one point that satisfies any of this, and so when we solve it, we're just going to get this point back again. But we'll just end up now with this point on our Pareto frontier. And then what we can do with the lexicographic method is we can do all different permutations of this ordering. So the ordering that we choose will get us a different point on the Pareto frontier. So we could imagine doing this process again, but first we minimize F2, and then we minimize F1 with the constraint added on F2. And we'll end up getting this point on our Pareto frontier. And so you can imagine if we have more objectives than just two, as we switch up the order a bunch of different times, we'll get different points on our Pareto frontier. What questions do you have on that?
But we only get the endpoints, right?
I think at least in this case, you only get the endpoints, yeah. Yeah, you definitely don't get all of the points on the Pareto frontier doing this.
Would there be any cases where we would get more than the endpoints?
So the question was, would there be any cases where you get more than the endpoints? I'd have to think about it. Yeah, I'd have to think about it. I'm not sure.
Not very helpful, right? Is this very helpful?
Is it what?
Is it helpful? We don't get the frontier at all, right?
Oh, well, you can get some different points on it. I think so. You can imagine if you had a point that was weakly so there's this notion of weakly Pareto optimal where like this would be like a straight line or something like that. You might get different points along like that. Yeah, I don't know, I'd have to think about it. I think in general, like if you have more objectives than just, go ahead, what's that?
Even if we had this,
Mm-hmm.
we'd only get
You would only get 1 point, yeah.
still 1 point.
Yeah, I'm just not sure you would get the end point, but yeah. Yeah, good question. Any other questions? All right, yeah. So we do want to get more points on our Pareto frontier. I feel like that would be nice. So here's one method that we could use that would get us more points. And that's the weighted sum method. So I don't know about you, but when I like first saw multi-objective optimization, I thought that this was like all you would ever do. I was like, of course, you would just weight them and sum them together. Seems like a very obvious thing to do, and it does actually work quite well. So the weighted sum method, basically you just turn it into a single objective optimization problem by just adding weights to each objective, depending on like sort of maybe how much you care about each one. You give a higher weight to ones that you care about more. And then you just sum them all together, and now you have a single objective to optimize. So in this case where we only have 2 objectives, we're just going to get something like this, where we have W1, which tells us how much we care about F1, and then we have W2, which tells us how much we care about F2. Okay, so just to test your understanding here, okay, so if W was 1, 0, so our W1 is 1 and W2 is 0, which point are we going to get on our Pareto frontier? Yeah, exactly, the one like furthest over this way. Because we're basically saying we don't care about F2 at all, so we just are going to optimize F1, and we're going to get this point here. Similarly, if it was 0, 1, we'd get this point over here, because now we don't care about F1 at all, we only care about F2. And then, you know, if we're like somewhere in the middle, we'll get somewhere in the middle, basically. And you can imagine that if, you know, you just keep changing the relative weightings in this vector, we're going to be able to like fill in the rest of this Pareto frontier. So this allows us to actually get like all these points that we were missing before. But actually only sometimes. So there is a case where this won't work. And to illustrate that, let's think of this from kind of a slightly different perspective. So another way we can kind of visualize the point that we get when we solve this single objective optimization problem is you can imagine you kind of draw a line from the origin, and it has slope W2 over W1. And then you draw a line perpendicular to that line. And then you basically imagine pushing this line outward until it touches the set of feasible points, or the set of feasible objectives. And then the point where it touches will be the point on the Pareto frontier that we would get for that particular weight vector. And so this, I promise this is going somewhere. So basically now, let's imagine that we like changed up this set of feasible objectives. So now we have like some other optimization problem, some other multi-objective function, and we have a different set of points that are possible. And this is now non-convex, to kind of go back to what Arik was talking about. We could draw a line here, and it leaves the set. Okay, and so the problem here is you can imagine we do the same thing where we like push this line outwards towards the function, and you can see we're like never going to enter into this region here, because we're only going to get these kind of points out here. That's as far as we can get, and everything inside here, the weighted sum method is just going to miss, because there's no way that this line is ever going to go past these points on the outside here. And so we're never going to get these points with the weighted sum method. And in general, like the weighted sum method will actually miss points on non-convex Pareto frontiers. So that's one issue with this method. Any questions on that? Yeah.
Convex is this like enough that you would pretty much always want to use?
Yeah, I think if you are convex, this would be the weighted sum method would be a good idea. Yeah. Any other questions? Okay. Okay, so no worries, there is a way to fix this. And we can use something called goal programming. So the idea with goal programming is we set some goal point. So for example, a lot of times you'll pick this to be something called the utopia point, which is like the best possible point you could ever hope for. So for example, in like the aircraft collision avoidance example, no alerts, no collisions, that's like our utopia point. It's probably not achievable, but we'd like love to have that happen. And that's what we would typically pick for our goal point. So we're just gonna pick some point like Y goal. And then all we do is minimize some like LP distance to this goal point. And we can change up P. So basically we're just saying like, let's find the point in our feasible outputs that is closest to this goal point. Okay, so to visualize this one, we'll start by looking at like kind of level sets of this distance by basically saying like, what is all the, so like everything on this purple diamond here has the same L1 distance to our goal point. And basically we want to find the point in this set that has the minimum distance to this goal point. So to visualize that, you can imagine we just kind of like expand out this diamond until it intersects with our feasible set. And then we get this point here, and that's what we would get for this goal programming objective. But we don't just have to use the L1 distance. We could imagine we use the L2 distance. So that would be like a circle like this. We expand that out until it touches our set, and now we get this point here. Or we could go all the way up to like the infinity norm, which is just like the maximum of any of the objectives. And then we can, it looks like this square here, and we can expand that out, and then we get this point in the middle here. And so you can see doing this goal programming, we actually were able to get to these kind of regions inside of our non-convex portion of the Pareto frontier. So that kind of solves the issue we were having before. But it did only get us like these 3 points. So we might want to be able to get like more points with this. And so then to do that, we basically combine this idea of goal programming with this idea of like weighting our different objectives, and then we can kind of get the best of both worlds. And so we have this thing called the weighted exponential sum method. And it might at first not really look like what we were doing before, but it's almost the exact same thing. So the idea here is like, instead of having a norm, we just raise to the power of p. So we're just, instead of like raising to the power of p and then taking the root with p, we're just raising to the power of p, but we almost still have a norm. We still have like kind of this distance thing going on here. But now what this allows us to do is like add weights to each component in that distance. And so now we can, just like before with the weighted sum method, say like, we care more about like, you know, F2 than F1 or et cetera. And so the way to maybe visualize this, if it's not clear, is before we had like all of these different norms that we were like expanding out to find these points on our set. And what you can imagine this doing is it kind of just like stretches these shapes depending on what W is. So for different W's, it'll stretch in like different directions. So maybe, for example, it's stretched in this direction for the W that we pick. And then you can imagine expanding all of these out, and then we get 3 different points on our Pareto frontier. And so you might be able to imagine if we like change up W a whole bunch, we'll get a whole bunch of different points, and some of them will actually be in that non-convex portion of the Pareto frontier. Any questions on that?
Will this get everything?
No. So varying P is actually still not guaranteed to obtain the complete Pareto frontier, but no worries. If we take the limit as P approaches infinity, we get something called the weighted min-max method, which can provide the complete Pareto frontier or the complete Pareto optimal set if we scan over the weights. So if you want to see it, it just kind of turns some things into a min and a max, and you can like check that out in the book. It talks about it.
That weighted exponential method, we were not only varying P, we were also varying W, right?
Yes.
So we could have varied both of them and got the...
Yeah, I think, well, so if you actually, basically what this is saying is like, if you set P to infinity already, and then you vary W, you will end up getting, yeah. So I guess this is almost like a specific case of the weighted exponential sum where you basically like take the limit as P approaches infinity.
Also, that first method could have done everything for us, right? The constraint. Because every time we get the leftmost point for us.
I think maybe in this example, yes. I'm not sure if like always that's the case. I would have to check. Yeah, good questions though. Yep.
It's kind of a silly question. If we can come up with a function that weights all the different f's in the way that we want, why do we care about finding the full Pareto frontier?
Great question. So the question was like, well, why don't we just come up with a function that like weights everything in the way we want? Why do we care about the full Pareto frontier? Actually, at the end of the lecture, we're going to get to that. We're going to be like, yeah, well, at some point we got to pick a point, right? So if we just know what point we want to pick, like, let's just go for that. And you absolutely can do that. I think the idea is that like sometimes you're in a situation. So like I know, for example, when they were developing ACAS-X, the collision avoidance system, they have a bunch of stakeholders at the FAA, and they don't necessarily know what they want, or they just want to know what's possible. And so a lot of times you just kind of want to know what's possible before that. But you're absolutely right. Like you could just, at some point, just pick a point and go for it. Any other questions? Yeah.
Is there a difference between taking the limit as p approaches infinity and taking p infinity?
Great question. So the question was, is there a difference between taking the limit as p approaches infinity and just saying p equals infinity? If I had to guess, this is probably like not mathematically defined correctly if p equals infinity. But yeah, I don't know for sure, so I don't want to say for sure. But yeah, I know that the book presents it as like taking the limit as p approaches infinity. Okay, any other questions? These are good questions. Okay. Okay, awesome. So that's kind of a bunch of different methods that are just using like a single design point and optimizing it. We can also adapt standard population methods. So these various populations methods you learned about earlier in the quarter, we can adapt those for multi-objective optimization problems. And there's kind of a bunch of different ways that you can do this. You can read the book if you're interested in like more of the details on it. Here's a figure from the book. So one example is like you might have this thing called a vector-evaluated genetic algorithm, which basically just extends genetic algorithms to this like multi-objective setting. Basically, the idea here is just that you have like these different subpopulations of your samples. And then basically you'll say like, okay, I'm going to take all the individuals in this one subpopulation, and I'm going to optimize those for the first objective. Then I'm going to have this other subpopulation, and I'm going to take all those individuals, and I'm going to optimize those for the second objective, and so on. And then what you do for the next step is you want to select parents from the different subpopulations to produce like the next generation of individuals. And so here's just a figure of the book where this happens. They just go across multiple generations, and it allows us to kind of get these points that spread out along the Pareto frontier. Another thing that's kind of cool with these population methods is you might be wondering, like, okay, how can I like rank these different individuals in a population if I don't just have like one single objective that I could use to rank them? And so one thing you can do is use this thing called a non-domination ranking, and I think it's like a super cool and simple idea. So basically, the only idea here is like we have all of these points here, and then we just want to say, okay, which of these points would form the Pareto frontier out of all of these points? So, for example, maybe it's this set of points here. These are not dominated by any other points in our set. And then what we're going to do is we're going to say, okay, we've got all these. Let's set them aside. We're going to ignore them from now. Let's say we just have these points left. And now let's look at what the Pareto frontier is. So it's this set of points here. And then we're going to be like, okay, let's set those aside. Let's look at what's left now. Get the new Pareto frontier. We get this set of points. And then we get the set of points that kind of remain here. And basically what we can do is we can use this as sort of a ranking. So for example, any point that's in level 4, well, it's got a pretty long way to go to get to the true Pareto frontier. And so we can say that, you know, this has a rank of 1 and this has like some ranking of 4. And it gives us an idea of like how much better one point is than another, which is kind of cool. Any questions on that? Okay. And there's 2 other things that you'll have to check out the book for on this if you want more information, but there's also this idea in the book of a Pareto filter, which basically, it basically just says, like, as you're running your algorithm, you might just want to filter out individuals that are like already dominated by some other point we've seen, because we know there's a point that's like better in all objectives than this current point, so there's no reason in like keeping it around. And then there's also these things called niche techniques, which sometimes your genetic algorithm could like run into an issue where you get these like small niches that are like spread out, or not spread out, basically they're kind of clumped together in different portions of the Pareto frontier. And these niche techniques help you like ensure that you get like an even spread of points along the Pareto frontier. Okay, but now we're going to get to this like ending portion here, which involves candy. And so basically, what we want to say here is, like, as we were talking about earlier, at some point we're just going to need to like pick a single design and go with it. Because even when they were designing ACAS-X, for example, like, yes, they might have traced out this Pareto frontier, they saw all of the different things that were possible, but like at some point they had to like put something on the airplane. So like at some point you're going to have to figure out what you want to go with. And so one very simple way to do this, which is kind of what was mentioned earlier, why not just like pick some weights, create a single objective, optimize for that, pick that point, and then we're good to go. And that's absolutely what we can do. But there's this question of like, how do we actually pick the weights? Because it'd be kind of weird if like they were designing ACAS-X and they just like went up to the FAA and they were like, hey, can you tell me like a weight vector that sums to 1 for your like weights of collisions versus alerts versus this? And they're gonna just be like, what? I don't know. And so one thing we could do instead is to do this thing called preference solicitation, where instead of just going up to them and being like, what's your weight vector, we can ask them kind of more simple questions. That's just like, which would you prefer? Would you prefer a collision avoidance system that has like this collision rate but alerts this often, to a collision avoidance system that has like these properties, and just ask them to pick one. And then from their responses to these questions, we can actually infer what their weight vector is. Okay, so we're going to do an example to see how this works. If you took 228V with me, you've already seen this before, but we'll do it again. So we're going to do this candy example. And okay, so first I need a volunteer. You should both like candy and have opinions about it. All right, any volunteers here? It will result in you getting candy, if that helps. All right, okay, so we have 3 different possible candies. M&Ms, Sour Patch Kids, and Skittles. And we're going to try to infer your weight vector over this candy, because it'd be weird if I just like went up to you and asked what it was. Okay, and so we're going to do so using these pairwise queries. So I'm going to offer you different combinations of candy, and you're going to tell me what you prefer. Okay, so first question here. Would you prefer a bag of 1 M&M, 3 Sour Patch Kids, and 3 Skittles, or a bag of 7 M&Ms, 1 Sour Patch Kid, and 2 Skittles? The first one, okay. All right, we're going to do some writing here. Okay, so basically, I picked this one. And so we know then, or at least we're making this assumption, that means that weight vector times, we'll call this option A, this option B, times option A will result in a higher value, a higher objective, than her weight vector times option B. So that must mean that W1 times 1 plus W2 times 3 plus W3. I definitely wrote that wrong. Hold on. These are both supposed to add up to 10. Hold on a second here. I think this should be a 6. Do you still prefer A? Okay. All I did was give you 3 more Skittles, so I think it's okay. Okay. Okay, cool. So plus W3 times 6. We know that that's greater than W1 times 7 plus W2 times 1 plus W3 times 2. Okay. So now we can just multiply these out, kind of like move some things over to the other side. So we'll get minus 6W1 plus 2W2 plus 4W3 greater than 0. And then we also are going to add this like extra constraint, which doesn't really constrain anything It still allows like all possible things to be true, but we're basically going to say W1 plus W2 plus W3 is equal to 1. So that just kind of constrains us to have this like relative weighting. And so then that allows us to say that W3 is equal to 1 minus W1 minus W2. Nothing crazy here, just rearranging. And now I'm going to go ahead and plug this in for W3. So we'll get negative 6 W1 plus 2 W2 plus 4 times 1 minus W1 minus W2 greater than 0. And if we keep doing a bunch of math here and simplifying it, we're going to end up getting something that looks like 5W1 plus W2 is less than 2. Okay, so this is just like a linear inequality now. And actually, this basically, we can call it a half space. I think you guys already learned about half spaces in this class, maybe? Okay, I don't know. Basically, it kind of divides. You can think of it as like a line or a plane that like divides space such that on one side it does satisfy this inequality, and on the other side it doesn't. So this is basically a constraint now on Allie's space of possible weights, because we know that her weight vector must satisfy this inequality. Okay, so I'll do a little demo here on the computer to show you what this looks like. So, okay, let's go here. So before response, we basically just said that this is our space of possible weights. We have W1 on this axis, W2 on this axis. We just imposed the constraint that W1 plus W2 plus W3 has to equal 1. So that means none of these weights for W1 and W2 are possible because they sum to something greater than 1. And so this kind of space over here that's not shaded in is the space of possible weights we have to start with. And basically, we want to add some constraints to this space in order to figure out what her weight vector is. So the first question we asked was this like 1, 3, 6 versus 7, 1, 2. And she replied A. And we just computed what happened there. We said we would get this half space where it must be true now that 5W1 plus W2 is less than 2. And so that's actually what, if you kind of look at this line closely, you'll realize that like this line here is basically where that thing holds with equality. And then on this side is everywhere that this inequality holds true, and on this side it does not. So basically what we've done is we've like reduced the space of possible weights that it could be. And now you can imagine we'll just continue asking these questions, and we'll continue to kind of reduce the space here. Okay, so let's ask a few more questions. So would you prefer 6 M&Ms, 1 Sour Patch Kid, and 3 Skittles, or 5 M&Ms, 2 Sour Patch Kids, and 3 Skittles? B. Okay. All right, so that gave us a new plane. We're not going to actually go through the calculation here, but we would do basically the exact same calculation we did before with these new numbers, and it gives us like a new half space that further constrains the space of possible weights. Okay, let's do the last two. Number 3. A. Okay, and number 4. B. All right. So now we have further constrained the space of possible weights. So you can imagine we could just keep doing this for a while, but we don't want to make Allie work too hard here. So we'll just stop here. And now this is kind of the space that's left of possible weights for her to have. And so once you've kind of narrowed down the space, there's various things you could do to pick a single weight vector and go with it. You could just pick the center, do something else. We're just going to eyeball it here because that's the easiest thing to do. So I'll just say 0.2, 0.6 looks pretty good to me. So we're going to say W1 equals 0.2, W2 equals 0.6. So that means W3 must be 0.2. And then given this weight vector, we can now give this new query, and we can calculate what her objective likely is for this query. So we can do this new weight vector times A, and then this new weight vector times B, and see which one is bigger. And then that will tell us which one we think that she would prefer from these two. And it looks like it came out to being A. Were we correct? Yay! Okay, so no worries. I have both of these. And I will give you the one that you picked after lecture in less than a minute, a little over a minute. Okay, just a couple things to wrap up. Okay, so in this case, we kind of pre-selected all the queries we were going to ask. You could imagine we could do a lot better if we kind of picked the queries as we went along. So we like looked at her answer to the first one. We're like, okay, now we all have all this space left. Like, let me try to pick a better query to like further divide this space. Another thing that didn't happen here, but we were assuming that expert was like perfectly rational. So like, it's always going to pick the one that she prefers. But like, as these queries get more complicated, that's not always so easy for like humans to do. And so a lot of times we like instead maintain a probability distribution over these weights and allow people to like be wrong every once in a while. So yeah, those are like 2 follow-ons you can look into. This is still a very active area of research. If you've seen RLHF, now you have like a very, very, very small inkling of like the things that go on there. And yeah, so that kind of wraps up multi-objective optimization. All right.